So in this tutorial, we'll be talking about the shift reg. The verilog code can be found there at projectfpga.com/shift register. This is the verilog code. I'll be explaining this code using this logic sim circuit. So the MMI has two main signals, the MDO and the MDI. The MDO is the output signal. During our last tutorial on output control, we saw how this MDO is being generated here. It was generated from this shift bit. This is the shift bit that gave out the MDO. So here, as this shift reg, we are going to see how this shift bit is being generated. So I'll divide this in two parts. This lower part here is used to generate the MDO, which is the output, while this upper part is used to process the MDI. So the MDI and the MDO fuse together to make up the MDIO bidirectional data signal. The two are combined together, but the separation comes from this enable signal here. You can remember when we generated this from this clock gen. This is where it comes from. So at this shift reg, we are using it again. We'll be using it here at this shift reg. So this MDCEN, whenever is 1, whenever it's high, is taking this data here, which is this lower part, and this lower part, taking this lower part, everything here makes up the MDI, the MDO. When is 0, it takes this upper one. This upper one is the MDI. So, and this enable signal controls two other multiplexers. So that is 1, 2. That is 1, 2, and 3. So whenever it's 0, it's taking in the it's processing the MDI. 0 is processing MDI, and whenever it's 1, it's processing the MDO. So here, when it's 1, nothing happens. It just latches the input. Here is the same thing, is 1, it latches this input. When it's here, it latches this input back. When it's here, it's now taking this lower, data, and this lower data makes up the MDO output data. So this PRSD is where the MDI is stored temporarily. So whenever the MDI comes in, it's stored temporarily in this RAM 8, and after a while, it's taken to this PRSD. This is the MDI. So this last byte is what this last byte do is that it takes the 8-bit data here and sends it here into this PRSD. That is basically what the last byte does. So whenever this is 8, when the 8-bit RAM is filled up, the first bit of this last byte comes on and fills the lower part of this PRSD. And whenever another 8-bit fills this RAM 8, the second bit of this last byte comes in and fills up the upper part of this PRSD. And whenever it fills it up, it's stored in the register model. When we'll be talking about the register model, see how it's being stored. So that is basically what it does. Now, whenever this PRSD has been latched completely, that is, the lower bytes have been filled and the upper byte has been filled, but this RG, this RGAD is equal to 1. the link fail is going to come up. That is, the link fail is going to be 1. It means that the address is invalid. This algorithm means register address. This file add means physical layer address. So all this, the file address, the register address, and this control data are all stored in the register module. They all come from the register. So whenever the register is invalid, the register address is invalid, this link fail comes up. This file address keeps record of the address, the physical layer address of the host we are using. So now this write up means when it's on, it means there's a write operation. When it's off, it means there is a read operation. So all this together makes up the data that will be sent out through this shift bit, and this is what makes up the MDO output bit, while the MDI input bit will be stored here temporarily. Everything for the MDO, the output, comes from the register. Everything here comes from the register, and they will be sent out through this shift bit to the MDO and down to other hosts on the network. So this is the basic explanation of the MDI and the MDO. So remember how this, when is 1, is storing data. When is 1 is storing, when is 1 is storing data to be for the MDO, and when is 0 is storing the MDI, data. So let's take a look at what makes up this MDO, this output data. So at first, it consists of the 16-bit control data. So the MDO is going to send out first the 16-bit control data. This control data comes from the register module. Then after that, it first of all sends them byte by byte. The lower 8-bit first goes out, then later the upper 8-bit also goes out. Then after that is another 16-bit. So the first one consists of part of the file address, the register address, and these two. These two simply represents in binary 1 and 0. So 1 and 0 marks the beginning of this transmission of this second phase. Now after sending this 8-bit, this is 1, 2 plus this 5-bit here, 7, making a total of 7. Then the LSB of this file address, making it a total of 8. So this is where this is a splitter. This is a splitter where they are all combined together. Then later, this is another 8-bit here, consisting of 4 bits from this file address, 2 bits from here, and then another 2 bits here, making it a total of 8. So for here, whenever the write operation is on, here is going to give you when the write operation is on, you are going to get a 0 and 1. When it's off, it means a read operation. You are going to get a 1 and 0. So this is what distinguishes between a write operation and a read operation. Then last, you have this one. This one here marks the end, and 1 is a 2-bit. It's 2-bit, so that is a 0, 1. So a 0 and 1 in binary marks the end of the transmission of the control. So that is what makes up the control data, the control signal, which is the MDO bits that are being sent on the file address. So I'm going to show you also how we generate these two signals, the large byte and the byte select signal. we already know that this output stores the MDI temporarily through the help of the latch byte. So what the latch byte does is, once the bit counter counts up to 8, it knows that it has received 8 bits of the MDI. So one of these comes on, one of them comes on. Initially is 0 0, so the first bit comes on, 0 0, the first bit comes on, and then it turns this on and then takes the 8-bit address from this RAM 8 here, takes the 8-bit, goes through here, and whenever this is 0, when this is 0, lashes it in here, and then when it counts another 8 bits, goes off, then this one comes on again and takes the remaining 8 bits and lashes it into this PRSD again. So as you can see here, what it's trying to do is, when this one is 1, this is the data here, this is the data here. So it tries to latch only the lower bit. When it comes on, it lashes only the lower bit and retains the original state of the upper bit, the same as here. When it's lashing the lower bit, it retains the original state of the upper bit. When it's lashing the upper bit, it retains the original state of the lower bit. So this is how the latch byte helps to store the MDI input. So I'm going to explain to you how this latch byte and this byte select are being generated next. So it has been generated from here. So the code on this website will explain more on how these things work, but I'm trying to make you understand it more. Now let's go down here. Now this is where the byte select is being generated, and this is the latch byte also. Now this is the bit counter. We use this bit counter when we are talking about the output control. This is this bit counter that does the counting. It does the counting. So this is where it's being generated here, and this is also this, with the help of this bit counter, that we are able to generate this byte select. With the help of the bit counter, we generated the byte select and the latch byte. So how do we do this? Now let's see how this bit counter counts. First of all, is a RAM 7, is a 7-bit counter. This is RAM 7 here. It's just made up of 7 different flops. It stores whatever input you are giving here, whatever input you give here. Then once the clock, you see the output is 0 0. So once you clock it, the output takes the value of input. So the RAM 7 is a 7-bit storage. So in verilog is the same as when you say register. So that is it. So wherever you see the RAM, it means a register in verilog. So here, the bit counter is a very important counter here. So let's see how it's being generated, and let's see what the output does. First of all, it's being latched. That is, it doesn't return to 0 when nothing is happening to it. It retains its original value. That is, it's being latched here. So the clock we use here is the main system clock, but it's being controlled by this MDC in enable clock here. This is what allows the value to increment. This MDC in, we saw where when we generated it from this from here, the clock generator model from the MDC. So it is the negative edge. It serves at the negative edge of this MDC clock. negative edge of this our main MDC clock here. So let's go back and see what it can do. So this first multiplexer latches the input and is only allowed to increment it only when this MDCN comes on. Whenever this MDCN is 1, it takes the value here. If not, it latches this input here. It's been latched here until this MCN enable comes on. That is when this bit counter is allowed to increment. Then this second multiplexer, this is what turns it on. Let's see what turns it on. There's a bit here called in progress. I mentioned about it earlier. In progress. In progress shows that an operation is in progress. Either a read operation is in progress, a write operation is in progress, or a scan operation is in progress. So whenever in progress is on, whenever an operation is on, data is allowed to increment. If not, when this in progress is 0, the bit counter is steadily 0. So when the in progress is not on, it makes the bit counter to be 0. So it cannot increment. It's steadily 0 until this in progress is on. Then data is allowed to increment. Then this third multiplexer here, this multiplexer, let's see what turns it on. This select bit here. This AND bit is used to turn this multiplexer on, and this AND bit says when the bit counter is equal to 0, that is here. This is a comparator that compares the bit counter value with 0. It says when the bit counter is equal to 0 and when there is no preamble is selected. That is when you go to the register and turn this signal no pre or off. When you turn it off, it means no preamble. But when you turn it on, it means preamble is allowed. So when there is no preamble and the bit counter is at 0, turn this on. Automatically sets the bit counter to 21. So why does it set this 21 is in hexadecimal? When you convert it to decimal is 33. That is, start counting from 33 when you do not allow preamble. Why does it do so? Because when the preamble is allowed, the preamble counts from 0 to 32. So therefore, when you don't allow preamble, starts automatically from 33. Don't count 0 to 32 is used to count for preamble only. You get? So when it's 0 and this no preamble is on, that means you don't allow preamble, start counting from 32. But in a situation whereby you allow preamble, count preamble. Preamble is only counted from 0 to 32. So when there is no preamble, automatically starts from 33. So that is what this third multiplexer does. So whenever you reset this bit counter and there is no preamble, it starts from 33 instantly. So if not, increment this. So here this is a adder. It increments the bit counter by 1. So this is how this bit counter functions. This is how it's being incremented here. So this is the process of incrementing the bit counter. So then let's see how our byte select and our last byte value is being enabled. So we remember that in this shift register, that whenever the first bit here, that is, let me set everything to 0. Whenever this one, the first bit of the byte select is set to 1, that is, it comes on. It allows the lower data value of this control data to be latched into this RAM 8. When this one comes on, the middle one comes on, it selects the upper 8-bit data to be latched into this RAM 8. Then when this third bit here comes on, it allows only this particular part, that is only this part, to be latched into this RAM 8. and then last but not the least, when this fourth one comes on, it will now allow this to be latched into this 8. So let's see how each of them comes on and off. And mind you that only one of the byte select signal can be on at a particular time. So these four byte select outputs, one thing we are going to notice is that they are consist of these AND gates, and for any of them to come on, this is the in progress here. Okay, no, this is the in progress here. For any of them to come on, the in progress must be on. That is to say, for any of these byte select signal to come on, it must be either a read operation, a write operation, or a scan operation. See, the in progress is in every signal, in every single signal. So if the in progress is off, none of the byte select signal is going to be on. So that is what essentially the in progress does. It marks that a particular operation is in progress. Now when does this first byte turns on? It turns on under two conditions. This OR gate makes these two conditions. That is, either when the no preamble is set, that is, there is no preamble and the bit counter is in 0. Once the bit counter is 0 and no preamble is selected, it means turn this on. This marks the beginning. When there is no preamble and is in 0, it marks the beginning. And whenever this situation occurs, it jumps straight to 21. That is 33 in decimal. Start counting from 33. Then, or when there is preamble, that's when you turn it off, it means you allow preamble, and it has reached 20. 20 is 32. That is, the preamble part has finished counting. That is, when no pre is negated here, it means you allow preamble and you've already counted 32. That is here. See, this is 20. 20 in hexadecimal is 32. Whenever is equal to 32 means you are finished counting 32, and that 32 allows the preamble to be counted. That's why you can turn it on. Either there is no preamble or there is a preamble. And this AND gate here now, make sure that is in progress, and operation is in progress before this first byte can be turned on. So now, when do you turn on this second byte now? The second byte comes on when 1, the in progress has to be on, and 2, the bit counter has counted up to 28. 28 means, let's check what 28 means in binary. 28 in hexadecimal means 40. So from 32 to 40, that means it has counted 8 bits. That is, after 8 bits from when this one come on, turn on this one. You know, this one came on at 32. Now this one comes on at 40. That means after 8 bits, turn on this second one. Then let's see about this third one. This third one has 3 different conditions. One is that in progress you have to be on. 2, the bit counter has to be 30. 30 hexadecimal in 30 hexadecimal means 48. I know this one, the second one came on at 40, and this one is coming on at 48. That means after another 8 bits. So likewise, this one comes on after another 8 bits. So, but the third condition is this, that there must be a write operation. This is the third condition, that must be on for this remaining 4 to be on, and that condition is this. Let's see what that condition is. Let me know where it comes from. This is it here. It must be doing a write operation, only doing a write operation, that this remaining 4 is going to come on. So if you are reading or you are scanning, you can turn on these ones. You can turn on those upper ones. So let's see them in practice here. So that's essentially what it's doing here. So after preamble, turn on, after preamble, that is from 0 to 32, turn on this one, that is this bit here, turn it on. Then after another 8 count, at 40, turn this one on, then at 48, turn this one on. So what is essentially doing is receiving this data 8 bits by 8 bits. So this is the first 8 bits, another 8 bits here, then there's the first 8 bits is the lower 8 here, then the upper 8 here, then another 8 bits from here, then finally the last 8 bits from here. And we know that only these two comes on for all the operation. The last two comes on only for write operation. That is, doing reading operation is likewise sends its own control data. So sending control data is compulsory. The sending host must exchange this control data. For doing a write operation, that is when it sends this remaining 2 here. That is when it is able to send these 2. Because why will it send these 2 during a write operation? It has to tell the other host that this is my address, so that when the host is receiving data, it knows where the source address, where the data is coming from. So this is what the MII model does. It exchanges this data, and mind you that this control data is not the actual data. These data are used for configuration purposes. So that is why this MII model, that is what this MII model does. Basically exchanges the control data. So we'll now see how this last byte, let's see how when this last byte comes on. So okay, so let's see how when the last byte comes on. So this is the last byte here, this is it here, and it turns on, it comes on from here. The last byte starts from here. Let me show you from here and here. So whenever this clocks on and off, this data from here moves to these 2 flip-flop, this flip-flop and here, and from there they go down to here and here, and that is where from there they move into this. Then on the next clock pulse again, they move into this last byte here. So it all starts from here. This is the condition that sets them from here and here. They move into these 2 multiplexer. When this clock is enabled, they move into the flip-flop, this one and this one, and from there you enable the clock again. Then I move into here and here. So the last byte upper bit and the lower bit, this is where they are being generated. So let's see the conditions for them. The first condition is normal. The in progress must be on. That is, an operation must be currently on before you update the last byte. Then 2, this operation, this 2 is that this operation must not be a write operation. You see that during a write operation, this is a write operation here. This and this signal here is noted. See, this is the write operation here, and here is being negated. That is, you are only allowed to latch the byte, that is, receive the byte and save them only during a read operation. That is when you are reading, because when you are writing, you don't save, you don't read. It's only when you are reading that you are able to save in this, you are able to latch the MDI into this PLSD. But when you are writing, you don't latch them. You only latch them doing a read operation, and that is what it's trying to tell you here. This is a write operation, and this is a write operation, and it's being negated here. So it means only when when there is no write operation that you are allowed to latch the bytes. So let's see the third condition. So to latch the first bit, it must be the counter must be 3F. Now let's see what 3F means in hexadecimal. 3F in decimal means 63. That is 63 minus 32. 63 minus 32 means 20. Okay, means 31. That is because 32 already from 0 to 32 is for preamble. So the remaining 31, after counting 31, we're able to latch this, and the other one is 37. Counting another 7 counts from 31. So this is essentially what we've been talking about. So after every 8-bit count, each of these byte select comes on after starting from 32, because from 0 to 32 allows the preamble. So plus 8, you turn on the next one, plus 8 the next one, plus 8 another one, plus another 8, you now latch it again, another 8, you latch it again. So that is basically how the latch byte and the byte set. And mind you, you only latch only when is a read signal. That is why there's a NOT gate here. This NOT gate means it's not a write operation. Therefore, it's either a read operation or a scan operation. A scan operation means continuously reading. You are scanning for changes in the control output. So this is how this shift register works. So we've talked how all these data are being organized, sent, and received. So by the time you read the code, for people who understand the code, you'll be able to understand what we've been trying to explain. Please kindly subscribe to my channel for more tutorials. Thank you.